What's up, everybody? Welcome to Earth Science. Next in our trip through rocks, sedimentary. So we looked at the rock cycle once already. That thing. Here it is, just the top half, because that's what we need for sedimentary. Guess what sedimentary rocks are made out of? It's right in the name. Sediments. For the most part. Little parts of it can get a little funny, but you guys are going to figure that out. So we'll get there. Generally, sedimentary rock is formed by deposition of material at Earth's surface, at or near. Um, Usually within bodies of water, that tends to be where most deposition took place. A lot of what I'm about to say here in this quick video, hopefully quick, is review of what we did back in weathering and erosion. That's all part of this cycle. And in fact, you can see it right here on the rock cycle, weathering and erosion. You take a rock, you go through weathering and erosion. That's the first part of it. Phone call, quick pause. All right, we're back. Sorry about that. So yeah, generally deposition is going to happen in the water. Can it happen on land? Sure, sand dunes. But usually within water, close this thing, this sediment gets buried and then goes through basically what's written in the rock cycle right here. If you want to be lazy, just write an arrow, but I'll write it. Compaction, which means it gets squished. I have a piece of sandstone right here. So sandstone's made of sand, right? That's it. Take sand and compact it. And the way that's going to happen is that more and more and more sand gets deposited on top of it. And cementation. What that means is that as the water that's being squished out of this leaves, there's minerals in water. There's minerals in all water, dissolved minerals. And they can act as a cement to like glue together those grains of sand, essentially. Okay? And it's how you go from sand. Y'all know what sand is. This is sandstone. You'll feel it when you do the lab. It's kind of like intuitive. It makes sense, like that this stuff can turn to this given enough pressure to squish it together. So really, to review where we were with weathering and erosion, I mean, we did all this for like a month. All three rocks, any exposed bedrock on Earth, sedimentary, metamorphic, or igneous, can turn to sediment through the process of weathering and erosion. And then that makes sediments, sedimentary rocks, formed from these sediments. Right? So take any one of the other three, weather them down to sediments. All the arrows that point to sediments say weathering and erosion. Take those, deposit them, bury them, compact them, cement them, boom, sedimentary rock. Like, I know it's a lot of steps, but it's also given to you in the reference tables. Don't forget that thing's right there. So if you get handed a question on the Regents or on my test that's like, wow, this feels like, I don't know this. It's, yes, you do. It's sitting right there on the tables. You got it. All right, so what we're going to have, three basic types, clastic, chemical, and organic. The first type, clastics, are kind of what we've already been talking about. They are made from bits of other rocks. And my keyboard is not happy today. Let me pause it again. One quick moment. All right, we're back again. New keyboard. Plastics are made from bits of other rocks. That's what we call sediments, right? Sediments, literally tiny little bits of other rocks. And that's what makes up a clastic sedimentary rock. Chemical sedimentary rocks, a little trickier, made from ions, which means that we had a solution. So what the heck is that? We got to know what that means. What a solution is. If you've ever dissolved something, you've made a solution. So to say Kool-Aid, what is Kool-Aid really? It's a sugar solution. It's water with dissolved sugar in it. And then you dump in a little bit of food dye and you say, this is Kool-Aid, right? So solution is water with dissolved ions. All right, we'll look at that a little bit more, but we'll actually look at it in context of this experiment that we started doing way back when we did weathering labs with the salt water. If you remember dumping salt water into that big beaker, now it's time to finally talk about that, finish that experiment. Lastly, we have organic, which means made from life processes of some type, which we'll get into. So let's do those one by one. Look at the reference tables quick. Get you ready for the lab tomorrow. What we have, starting with the clastics, the clastic sedimentary rocks, the ones that are very literally made from sediments. Here's how this is going to work. Start with a little bit of physical weathering. Every single bit of exposed rock and soil on Earth is under attack from the atmosphere. Wind, water, rain, freezing, thawing, roots, all of that stuff that beats up on rock that we talked about in that unit. This really should be a review of what we did then. Physical weathering will create sediments, right? I'll say creates sediments. Those sediments then are going to get washed into rivers. I'm drawing a little happy little river here. Okay, so in the rivers, those sediments will get carried along. We had a word for that back in that unit. Hopefully remember. Erosion. And then those sediments get down to a body of water or something and get dropped off. Deposition, which is where we kind of stopped our story back in that unit. Well, now we're going to take it a step further. I'm going to blow up the corner of this down here to get a little bit more accurate. Sediments, once they hit the water, remember this thing? We did a whole bunch of work with how fast does water have to be going to carry certain size particles. So if it speeds up, it can carry bigger ones and move them more efficiently. It's called erosion. When it slows down, because like a river is hitting a larger body of water, it can't carry them anymore. It's got to drop them off. So in the big bodies of water is where those sediments will get dropped off. And we call that deposition. Okay. And if you remember this would be great if you remember this. This is something that can pop up. Running water is very good at sorting out the particles. The heavier they are, the faster they're going to get dropped off. That was the premise of the whole bead lab. The bigger ones settled faster. The smaller ones settled slower. Therefore, in currents will be carried further away. So you get a nice organized, sorted progression here of larger particles. And then you get out to sea to smaller particles, which is how geologists have been able to really piece together Earth's history. If I go in and find a piece of sandstone, this is sand, and if you were here, you could feel it, and you would have no doubt that it's sand. Where do we see sand today? Beaches, sand dunes, things like that, right? We know those environments. So when I pick up a piece of sandstone, and this is a sandstone from northern New York, Theresa, I'm holding on to an ancient beach. This is a beach, maybe 450, 500 million years ago, right? There was no people there, but it would have been a nice beach. It's white sand. Think of where you see white sand beaches today. There were white sand beaches in what would eventually be called upstate New York a long time ago because it was a totally different climate. And the planet, New York was actually tectonically in a totally different place. The rocks you see over at the Salmon River are smaller limestone, sandstones, and limestones, siltstones, and shales. They're made from smaller things, representing deeper water deposition because small particles, as we can observe today, get carried further out to sea. So this is what allows sedimentary geologists to go back and say, I mean, every single sedimentary rock that you see in that river cut down in town is like a page of a book telling us exactly what was going on at that time. In this environment, these particles get dropped off. And it's exactly that. Like you hold it and you're holding on to a piece of earth from a long time ago, literally like a book, like a history book. If I find this kind of sediment and I know what kind of environment that sediment settles in, then I'm holding on to that environment from a long time ago, pre-human by a long stretch. Anyway, that's just me getting excited here. What we're going to draw is, my black pen is missing, is really just that deposition happens, and deposition happens, and deposition happens, and that consistently goes on and on. I'll even put some down here below here to say that older deposition down here low happens. So if you're down here, if you're some sediment that's down here, You're being squished by all of that overburden, by all of the weight of the ocean, and then as that water gets squeezed out, some of the minerals get stuck behind and act as a cement to glue that together to form a rock. We have a fancy pants name for that word, for that process. And don't be scared. I know big vocab words can be scary. I'm going to show you where you can find it on the tables. You're going to be okay. Lithification. Lithification. That term means that basically that's the moment, that's the process where you go from sediment into sedimentary rock. It lithifies into that. Okay, it's this diagram, as much as it kind of looks kind of 70s ish, shows us that. Take loose sediments, sand, zoomed in, right? Microscopic image of sand. Have them pushed together and pushed closer together still with minerals cementing them together. And you got yourself lithified. You've got yourself a clastic sedimentary rock. And our only job with clastic sedimentary rocks is to say, well, what is it made out of? Sand, then it's sandstone. Silts, then it's siltstone. It's pretty easy. So let's pop down to the tables. You'll have to jump around in the notes a little bit here because I like to look at the tables one by one. Starting with the clastics. So yeah, we did clastics. Circle it with me. Clastics are these top 5 rocks on this table. We'll do the rest of these in a minute. And it's pretty basic. If the rock is made out of clay with a size that's that big, and hey, we remember the reference tables. This guy right here that we worked with pretty extensively. There's those sizes again. Remember, these are the 6 official particle sizes. Clay is 0.0004 and down. Silt is between that and 0.006. You don't have to memorize them. They're right there in your tables all the time. Well, here they are again. Clay, that size particles, when lithified, makes shale. Silt, those size particles, when lithified, makes siltstone. Sand, those size particles, when lithified, makes sandstone. These map symbols come up sometimes. Look for those. No big deal. The top 2, conglomerate and breccia, are made of this. So if we look at this, it says pebbles, cobbles, boulders, sand, silt, clay. There's all of our particle sizes, all mixed up. We had a word for that back in, especially when we talked about glaciers and rivers. Unsorted. So these 2 are unsorted deposits that create rocks that will then give you what we call either conglomerate or breccia based on rounded or angular. And that's it. Again, clastics, fragmental is a good word. They're made from fragments of other rocks. And that's it, right? That's it for clastics. 2 more to go. Good job so far. Chemical. All right, let me grab my experiments over here. Remember this thing? So in the weathering lab, I had different groups at different times putting rock salts into water, putting the cap on and shaking it, and then straining the water out, leaving the salt behind. That was clearly salt water. No tricks, no magic. It was just salty water, right? And I collected some of it in this giant beaker, and now we've for like 2 months, let that water evaporate away. And we've created rock. It's still a little bit wet, but come check this out in the classroom when you get a minute. We've created rock salts. We've gone from salt to dissolved salt back to salt by adding water so it dissolves and then getting rid of the water so it like undissolves, if that's a word, but which it's not. So this process really, look at the drawing. We're going to do the same thing that we just did up there. It could look just like plastic. The switch we're going to make in our heads is rather than like a grain of sand being weathered off, going into a river and ending up somewhere, it's ions, which is what happens. That's what you create when you dissolve. We could really use a little bit of chemistry ahead of this, but you guys don't take chemistry until next year. So what are you going to do? When you dissolve, you create ions. Those move downstream rather than literal sediments. Right? So like, here's what happens. You don't have to write this down here if you don't want. Salt is NaCl. That's the formula. It's on the back of your reference tables if you want to look at it. Halite. Put it into water. Stir it up. It dissolves. And when that happens, you end up separating it into separate ions. Sodium with a plus charge, chloride with a minus charge. That's what it looks like, quote unquote. I mean, you can't see it because they're individual atoms, but that's what it would look like in water, separated. Then, when the water starts to go away, it's got to go back. It can't go off into the air, evaporating with the water. It's going to turn back into salt, NaCl. Okay, that's really the story. I mean, that's it. That's what this experiment was. We made a chemical sedimentary rock by dissolving it and then getting rid of the water. That happens in nature. Again, we're going to say kind of what we did up there, only instead of physical weathering now, chemical weathering. Chemical weathering happens when water hits the ground and soluble things dissolve. Soluble minerals is a better way to say it. There's that word again. I know it came up before. Soluble just means that it will dissolve. It's able to dissolve. This pool ball won't dissolve in water, but a sugar cube would, right? The sugar cube is soluble. And it turns it into ions. Those ions enter into the stream. There's my stream's looking a little funky this time, but that's all good. Enter into the stream, go out into the ocean, and they're there. I'm telling you, the Salmon River right now is salt water. It's not like ocean salt water, but very, very, very weak solution of salt water. There's a little bit of dissolved ions in there. Take those all and dump them down into the ocean where they accumulate and accumulate and accumulate out the St. Lawrence River through the Great Lakes, right? Make it to the ocean where they accumulate. And then you get to, especially in warm oceans where this happens a lot, because it's warm, wherever you get a lot of evaporation, those ions got to turn back to a solid, a la this experiment, just like this. We got rid of some of the water, the salt has to form again back into a solid. And the fancy pants name for that, I wish it was undissolves. It's not. It said it formed a precipitate from solution. Again, if that sounds like, oh man, scary science vocab, don't worry. It's in the reference tables. You're going to be okay. That would be how rock salt forms. There's layers and layers and layers of these salts. There's one underneath Cayuga Lake. The Finger Lakes, I already told you they were really, really deep. Even deeper than that, underneath the lake, there's a salt mine where there's big, huge layers of salt, and they're blasting it, removing it, bringing it up elevator shafts. And that's what we put on our roads, right? Those all formed from warm seas where the water evaporated away and the salt formed. Big, thick beds, just like it is in the bottom of that beaker. Cool. All right, so let's go down here and say crystalline. I really do prefer that they would have said chemical here, but say I'm not in charge. But these are our chemical rocks. Now, there's these scary words: precipitates, evaporites. I know that sometimes you get a question and there's all these sciencey vocab words, and sometimes you just like say, I don't know what this is talking about. The rocks test in particular is the one to not panic on, to be patient, and look at the tables until you find the words. If you see precipitates and evaporites and you say, I don't know, and you quit, you're wasting time because these are the ones. There's going to be hard questions. There's going to be some you miss, but there's going to be some that you can get. They're freebies because it's written right on the tables. So what are your precipitates and evaporites? Yeah, it's all that stuff, how that happens. But really, they keep the questions as simple as saying that, like, if it is halite that evaporates, you form rock salts. If it's gypsum that evaporates, when the water evaporates, you form gypsum. Dolomite forms dolostone. These minerals form these rocks. And the questions, honestly, like as complicated and scary as they will look, they'll be like evaporites. They'll give you one of those and like two of these and then an igneous. And so all you gotta do is pick the right one in the right spot, and you're gonna be okay. All right. If you can keep this whole undissolving mess straight in your head, then you're crushing it. Okay. Well, lastly, And thanks for sticking with me. Organic, made from life processes, with the classic example being coal. Okay. Um, at different times in Earth's history, there's been periods where there's been abundant forests, and especially in areas where it's kind of boggy and peaty. If those trees can die in those bogs and peats, they can get buried by other organic material, covered and covered and covered and covered and preserved. Everybody that's ever burned a piece of wood is kind of doing the same process, right? I burn firewood at my house for heat. I go to my woods, chop down a tree, cut it in pieces, and burn it, set it on fire, right? And it produces heat. You've all done it, right? You've all been by a fire. You know that fire is hot. You know that in wood, there's energy. There's potential energy to create all that heat. So this is the same deal. Take the potential energy of all these trees. Now, I wasn't there back in this time period with these giant crazy critters to cut down those trees. Nobody was. But they got preserved by falling into swamps and building up layer upon layer upon layer of this rich organic material. Now we can go dig that up and call it a piece of coal, and we can burn it for energy in the same exact way that you burn down a tree for energy, with a giant difference being that tree is maybe 350 million years old versus the tree in my yard that's maybe 30 or 40 years old. And then there'll be another giant difference when we think about the idea of what was in the climate then, carbon dioxide wise, versus what's in the climate now, carbon dioxide wise. But we're going to save all those arguments for later, because now all we got to do is say it's easy. Organic stuff falls down, builds up in swamps, and preserves that organic potential energy material. And it can form, and I got examples of this. You'll see it when you get to class. Of what happens as it gets to higher and higher and higher pressure, squishing more and more and more on it, and it's really pretty easy. Honestly, there's not a ton to talk about with it. So why am I babbling about it? Is that what you're saying? I hear you. Where is it? Bioclastic is the fancy name for it. Bio, life, plastic, fragments, right? Like life fragments. Coal is made of old trees, old plants. We expect to find a lot of carbon in it. That's why it has the potential to burn for energy. It is compacted plant remains. We call it bituminous coal. We'll look at another form of coal when we get to the metamorphic rocks where this stuff really gets compressed. All right. Almost there. Keep it up. Last little weird one is limestone. Our friend limestone kind of makes a mess. I could probably get out 5 or 6 different rocks that I know are all limestone and ask you to identify them, and you're going to try to call them 5 or 6 different things. Limestone comes in lots and lots and lots of forms. In fact, there are forms of limestone that can fit into all 3 sedimentary categories. Fortunately for us, this is a huge giveaway. If you remember the mineral lab, the mineral calcite bubbles with acid. So that takes all the stress away from it, from all the very different ways that limestone can look. Do the little acid test, which again, I'm not going to do with your rocks. I'll show you separately. Um, then you say it's got calcite, it's limestone. My job's done. Easy peasy. And that's what this blank is right here. All right, for you to take the lab then. The lab, we'll talk a little bit more about what you got to do. We're going to try to find all these. You can do it. But I would like you, the folks that we did this in class. Obviously, you're doing this because you weren't here that day. And try to answer those questions. I'm going to check them out before we say, okay, jump into the lab. Deal? Thanks for sticking with me, everybody. Happy Thursday, or whenever you watch this. Take care.